All right, welcome everyone. We are about to embark on the next chapter in these live coding sessions, and the goals for today. So we'll start with making a test bed for our simulations, which was a homework from last class. So in the last class, we finished with running a pandemic simulation on one network, but we want to be able to average different runs so that we have smoother curves that we can actually compare between solutions, for example. Then, the next step, we need to write a small world network creator. So in a Zoom meeting, we talked about this network, which is called Barabasi-Albert model, and it is a scale-free small world network that is believed to be closer to what real networks are. Because remember, in the past we created a network that has cycles, which we liked, and we created a separate network that tended to have overconnected nodes that have more than their kind of fair share number of connections. But we wanted to have both of these features, and we actually want to have more of this hubness, more overconnected nodes, because that's how real networks are. So this Barabasi network, while not ideal, is our best next step, I guess, so we will try to implement it. And then, once we have that, we can try to do to run some computational experiment. For example, one question that I thought is fairly easy to address is the value of like those low-hanging fruits of social isolation. So what if you take a network and remove just one node from it? But we will pick the most connected node. So we'll find this influencer or this large event that have hundreds of attendees or something like that, and we just cancel it, which in our model will be like finding the node, the most connected node, and removing it, or at least disconnecting it from the rest of the network. Will it have the effect on the average disease propagation in this network? So we should be able to model that. And then at the very end, I'll probably make it in a separate video, but there are some housekeeping items that we want to do. We have some functions that are not a part of our class that we may want to talk into the class, and then our class declaration is actually pretty long now, and it's getting quite stable, I'm guessing. It's not ideal, but it's like it works. So we may want to cut it out from a Jupyter notebook and put it into a Python model, and then just import this model as we do it with other modules. So we may try to do that in the end. Okay, but so let's start with finish catching up with the homework. So let's quickly look through the notebook that we have. I just created a copy of it. So the last notebook was like number 83. This is number 84. And I changed the goals for today, and that's the only thing that I did compared to what we had. So we import some stuff, then we have a graph, which is our class, and it has so creation, add node, add age. I'm mostly reminding myself what's going on, but okay. And then we can get a list of nodes. Yep, and then we can have a list of edges, and it generates a list of edges. This is for printing, so we can actually print it. This is for plotting, we can plot it, and it supports now. So it has two properties. One property is the dictionary of edges, and the other property is a list of values, and these are used to track the state for the disease propagation for the purposes of the pandemic modeling. And we should actually add a comment here that it's like 0 for healthy, 1 for infected. For now, that's all we have, right? Good. Okay, here's the test. It passes the test. Let me actually run that. So I will run this part. I will run this part. It passed the test. Then we have a separate function degrees that's just a function. It's not part of the class. And it calculates the degrees of the network and also plots a histogram. We have a random network creator, and that's basically RDosh like type 2 graph in which we have a fixed number of edges and we distribute it. So let's maybe move this comment into the document string. Let's create a random, okay, creates a random RDosh type 2 network with edges with NE equals NV. So I'm not sure this type 2 is an official way of naming that, but according to Wikipedia, this seems to be like, I think it's okay. Most people will probably understand what's going on. Okay, and it works. Does it work? Yep, it does work. It creates it. Here's what it creates. And then we have our alternative network creator, which I call Rich Club Network, which is not necessarily the best name because it's an unofficial way, and it's kind of halfway in between like random and Barabasi in the sense that it adds nodes one by one, but which means that, and for each node it connects it to the previously added nodes, but it didn't have cycles because each node is connected with only one edge. And so it makes it, because each node is connected to nodes that were there previously, it means that those nodes that were added earlier would be more connected. So it tends to create overconnected nodes, but not to the extent that we tend to see in real networks, in real world networks, where some nodes are ridiculously overconnected. If you think of like Instagram or like Twitter, there are some people who have thousands of connections because that's how life works, right? If you have thousands of connections, you're way more likely to be noticed by new users. And so people who have lots of connections tend to accumulate connections. And if you think of events, it's for a different reason, but similar dynamics might be in place. So if you think of like the number of events you attend, and then average number of people, if you think of your social interactions and the number of people involved in the social interactions, you may notice that you interact with one person, with two people, with three people, with two people, with three people. So you have these small talks or whatever, some sort of small interactions. And then suddenly you may have a class of 10 people, and then suddenly you may have like a church service or a concert of 1,000. So there would be few events with a huge number of attendees. So I'm not quite sure the same logic about the dynamics of creating of this network, of like the bipartite network of events and people, whether the same logic applies, but at least from the common sense point of view, you can argue that maybe the same statistics would be true, that very few events would have very high numbers of connections. And if you remember what happens during the pandemics, it's one of the first steps that states and countries and municipalities tend to implement, which is canceling concerts, essentially canceling parades and canceling these huge like conventions, conferences, because they may lead to a spike in disease propagation. So we'll try to model that. But okay, and so what's happening lower and lower after this thing? So this thing works. This is some pseudocode that we no longer need, and this is the pandemics, and the pandemic seems to work as well. Okay, all right. So let's start with like shaping this part, turning it into something that we can actually use. So we have the pandemic part. Let's keep here. Let's add a test here. So let's actually do the following. So let's take this part and copy it below. I'm pressing B, so escape B. I have a new cell. I copy it here. And let's only leave a test here. So the test doesn't need this figure and subplot, and the test doesn't probably need this number of cases. For the test, I only want to make sure that it works. So I want to create a new G, and G will be like whatever, rich club network. Say I'm making a rich club network relatively small, and then I propagate for only like 2 steps or something on this network, and I plot it. Okay, good. Or maybe, okay, 0.5. Yeah, so it seems to be working. It creates a small network and it propagates it. So the thing that we notice now is that, okay, let me do this thing. Number of steps 1. If you look at the node that is red now, it's always the fairly connected node. Like it's never on the leaf. It's always like in the center. Why is it so? Well, that's because that's the way we coded it. If you look at the node that is initiated as sick, our patient 0, it's always node number 0. And node number 0, by virtue of being the 0th node to be introduced, it's always overconnected because other nodes in this particular network, in a rich club network, because other nodes have high chances to be connected to it. But we probably don't want to have that because it's a huge assumption, and that's weird. It's not necessarily the most connected person who becomes the patient 0, right? I mean, in a small country with lots of travel, where the disease is much likely to come from much more likely to come from the outside rather than from the inside, maybe it will be the overconnected person because they will travel and they will have visitors from, I don't know, in their parties, in their palace. Some king will have a like ball and they will invite infected ambassadors. But it's not necessarily true for arbitrary network. So let's maybe make sure that we always make a random node for this patient 0. So instead of 0 here, we want to find a random number, a random node. So let's do that. So patient 0 equals, and we just take a random number between like 0 and the maximum number in the network. So it's like np random rand int low equals 0, high equals, it's like the number of nodes minus 1, right? So we had recently taken the nodes, we had recently asked our graph for a list of nodes. So let's do the following. Let's save the list of nodes into a variable nodes, and this is a list. And then we can reference this list here. We can also reference it here, so that we just don't run this method 2 times. So we'll reuse this thing, this variable again and again, and then total number of nodes is easy to calculate, just the length of this list. So high is the length of nodes, and if you remember, the way this generator works, it will never be equal to high. It's always between low. It's always equal or larger than low, but it's always smaller, strictly smaller than high. So everything will work correctly. Because of 0 in indexing, it will have values between 0 and high -1, including both. So yay, that's what we want. So this will be the number of the patient 0, and we'll set this patient to 1. Only, and we need to change that. Only one patient, only one node is sick, right? Okay, let's test that. Oh yeah, look at that. So now leaves, those nodes on the periphery, may become patient zeros. Good, that's what we want. So pandemics is done, the test works. Now let's do this computational experiment. So right now what happens is that we run a pandemic on a graph, and it's always the same graph. I mean, the graph is not even generated here, it's kind of inherited from upstream. And we run it, and then we plot it, we plot the final state, but the final state is everyone sick, so we don't care. We no longer need it. Let's just delete this whole part. Let's only retain history. Okay, now we have history, and history is different every time, and this is the number of new cases every day, right? But we want to have more of those, so we want to run lots of those. So okay, let's do that. N steps equals 30. So let's actually make n steps into a constant. N steps equals, sure, 30. N trials equals, like, how many trials? 20. And I'm making them all capitals because that's the standard for constants in Python. We want to have them in all caps generally. So let's do a loop for I in n trials, I mean in range n trials, n steps equals n steps. So that's already better. We have lots of curves, but that's not what we want. We want the average curve. So okay, how to do an average curve? Instead of just plotting every history, let's store all of them and plot the average. And we've done that before. We've done something like that before. So history will no longer be a vector. It will now be a rectangular, two-dimensional array. So it will be a numpy array. Let's initiate with zeros, for example, zeros. And the shape will be like vertically. Time goes vertical. Time, I mean, you can do it differently, but I always do it like that. So for me, time is always the first, kind of zeroth axis, and it goes vertical. And the trial is always the horizontal axis. So it will be axis number 1, which is actually second. I'm still not sure how to name them in a lecture, because like humans don't use zero indexing usually when they talk. But axis 0 is time, axis 1 is the experiment. So which means that we'll have n steps running down and n trials running right. And then instead of just pushing the results of this pandemics into history, we'll push it specifically into ith column of history. So we should take all rows, we should put a column to take all rows, but we'll put the ith column. Okay, and if we run it now, nothing changes. Even though plot is now outside of the loop, we store all traces and we plot all traces. But instead, let's plot the mean. So we'll do np mean history, and we just need to tell the np mean, numpy mean, which axis to squish. So if we squish 0th axis, we'll have average for each trial. Across each trial, time will die, trials will stay. That's not what we want. We want to squish it horizontally so that trials disappear, but time stays, which means that x is equals 1. Not 0, but 1. Oops. Of course, I didn't close the brackets. Yay, look at that. Let's go for a really high number of trials. Yay, we have a smooth curve now. Right? So that's great. Now let's think what's randomized here. The graph is actually the same, which is a problem. So we're not actually studying the properties of a certain type of a network. We're studying a very specific network, this network shown above. The graph is always the same. What's randomized is the process itself. So which nodes will be infected in each next step. If we go back to the pandemics, it's like this part that tosses a die every time the disease is about to spread. And also patient 0, which node is the first node to be infected, is also randomized. But we probably want the entire network to be randomized too. So we want to study the properties of a certain type of networks. So we want to regenerate networks every time. So let's copy that. Let's add it here. Let's rerun it. Yeah, so as you can see, the shape of the curve actually didn't change that drastically. We can make it even smoother if you want to. It will take a while. Yeah. Good. And that was a network of 20 individuals. Sure, let's park it for now. Let's go back to 100 trials so that it doesn't break later. Okay, let me think. Do we want it? So for now it's a script, it's not a function. Do we want to turn it into a function? Let's leave it as a script for now. We can always turn it into a function later. Okay, so that was part 1 of our homework. Now we caught up and we can go further. What's next? Write the small world network creator. Okay. Let's see. So, what are we talking about? Here's the process. Let me describe the process. The general idea of the Barabasi-Albert model is the following. You start with a node, then you add more nodes, but at some point you just go into a rhythm that goes like that. You add a new node, and then you connect it to previous nodes, which should sound familiar, but the probability of connecting to any of the previous nodes should be proportional to the number of connections it already has. So if a node has more connections, it will just keep hoarding them, keep accumulating them. Which means that we need to change at least one thing. And this one thing is this, like compared to our previous network generator that you've seen just now, that we've run just now, we need to change the probability of connecting to different nodes. But we will actually do another thing. We will switch to kind of the type of a network that's shown here on this picture. Instead of connecting a new node to only one node that was created before, we'll connect it to 2 nodes. So each node will be part of a cycle. It's not necessarily the most realistic assumption, but it's definitely more realistic than our previous assumption that every person has only one friend. No, it wasn't true. But that every new person is connected to only one, comes to this world connected to only one other person. So because in our previous realization, we would always have a tree, and that's not realistic. We want to have some cycles. So we will go a little bit maybe in the opposite direction in terms of exaggerating the amount of cycles. Every node will be part of a cycle, because every node will be connected to two different nodes. And if we want to compare, so we will do that. And once we do that, if we want to compare this network to the random network, to the Erdos graph, we'll have to change the number of edges there as well. Because right now the number of edges is equal to the number of nodes. And here I'm making an executive decision that we're moving to the realm where the number of edges is about 2 times the number of nodes. Not exactly actually, but kind of close to 2 times. Not exactly because of these few first steps. Few first steps are weird. You cannot connect the 0th node and you cannot connect the first node to two other nodes. The node number 2 in computer terms, or the third node in human terms, will be the first node to be connected properly to two previously existing nodes, right? Yeah, just think about it, look at the picture, read it. Saying this aloud is weird because of all this zeros. The third node is the first node, which is actually the second node. Like what? I'm sure you can get it. Even if you get confused, just stare at the pictures, read the text. Yeah, it's not rocket science at all. But the takeaway message is that when we code that, actually we should be careful about these first few, about node number 0, about node number 1, because they don't follow the same pattern. They're kind of an exception. The seed for the network is kind of weird. But that's okay, that's okay. All right, so what do we do now? Let's go and code it. Because the style of this network is not that different from our Rich Club network, let's modify this thing. So first, let me actually move this comment into a Docker string. Okay, let me now copy it. So I make sure I'm in blue mode, not in green mode. Then I press C and I press V and I have a copy. And then I will call this new function Barabasi. And this will be Barabasi-Albert's network creator. Number of nodes. N edges about 2 times by n nodes. So I will hard code it in a way where each new node, starting from some, is connected to 2 nodes previously existing. Because you could change that, that's obviously a parameter of the network, but for now I will hard code it. If in the future we want to play with the density of edges, we'll have to modify that. But that's easy. Okay, so what do? We create a graph. That's true. Then we need to change 3 things. We need to connect to 2 nodes instead of 1. We need to sample with different probabilities. Right now we have this random number generator that samples all nodes with equal probability, so we want to sample them with different probabilities. And the third thing, we want to make sure that the seed for the network, the first 2 nodes, are created properly. So let's start with this probability. How can we change the probability at which we sample nodes? Let's go and check what's even in the numpy sample. I've googled that before, so I have a really nice suggestion. Yeah, numpy sample randomly from a list. Let's see what we can do. Oh, look at that! There is a function, numpy.random.choice. Thank you, numpy, for having a function for us. numpy.random.choice generates a random sample from a given 1D array. And look, it even has, even this thing, so this is exactly what we need. And we actually can follow two different, we can do two different things here. There are two ways to solve this. Even with this function, it offers us two different ways to solve this problem. Because we want nodes, the probability of sampling each node to be proportional to the number of connections it already has, right? So we have two ways of coding that. One way is to explicitly, so to create a list of nodes, but also to create a vector, a list of probabilities. So for each node to keep track of its current degree of the number of connections it has and recalculate it into probability. So just divide it on the total number of degrees in the graph and then provide this function with this vector. And that's option number one. Option number two is to have a list of nodes, but then, and sample from this list with equal probability, but then have nodes that have many degrees overrepresented in this list. So it may sound weird, but okay, let me show you, like, let me use this thing as an illustration. So say if you want A to happen with, if you want some A to happen with twice probability of B, you can sample from a list that looks like A, B. Right? So if you do something like that, and you have a list, and A is represented in this list 2 times more often than B, but you sample one of the elements with equal probability, you will get A more often than B. Twice more often, right? Which means that, let me actually turn it into a command. So we need to sample different nodes with different probabilities. Fortunately, numpy has a function, numpy.random.choice. Let me give a link. That should help. Still, we have two options. We can explicitly provide a list of probabilities for each node, or we can keep a list in which every node is presented several times, namely the same number of times as the number of connections it has. All right. Which approach should we follow? Let's probably do the first. Okay, let's follow the first approach. Let's follow the first approach. We'll keep track of the degree of each node, and we'll update it, and we'll also keep track of the total sum of all degrees, and then probability of connecting to node I will be equal to degree of I divided by the sum of all degrees, right? Right. Let's do that. Let's do that. Okay. So originally we don't have this line, g equals graph, just creates an empty graph. Let's create degrees. Degrees are empty. Empty list. Should I use a list or should I use a numpy array? Is there a difference? Let me maybe use a numpy array of an empty list. The reason numpy is probably better is that I will want to sum it. So for this to work, I will want to run a sum of it, and it just make like I will be able to write this. I will be able to write this thingy as one-liner if it's a numpy, but not if it is a list. If it's a numpy, so numpy objects are better in this case. So degrees is numpy array, and for now it's empty. Now we need to create this seed for a network. So let's just, for now, let's explicitly code it. There are smarter ways of doing that. But for now, if we want to make this function really flexible, and we want each new node to have some arbitrary number of connections, then creating this seed may be a little bit tricky. We can do that, but it will just take a little bit of thinking and careful coding. But we are doing this for now. This one particular type of a Barabasi-Albert's network. So the seed is always the same. The first node just appears. The second node is always connected to the first node. 0th node always appears. The first node is always connected to the 0th node. And then after that, we switch to it like normal way. So for I in range n nodes, sure. If I equals 0, let's just add a node, sure. Elif, which is like else if I equals 1, g add edge from 1 to 0, yes. And then else actual preferential what? Connection? Preferential, there was a word. Whatever, connection. What was the word? Preferential attachment, preferential attachment. Actual preferential attachment. We'll come back here. So because we need to modify degrees. Add node 0. At this point, degrees can still be empty, doesn't matter. Here, once we are at I equals 1, and we're about to go to the next step will go into normal mode, we need to make sure we fashion the degrees vector properly. So degrees of 0 is now 1, and degrees of 1 is now also 1, because they're all connected to each other, and that's it. They both have a degree of 1, right? Okay, so this is like the base case of induction, and now we have this repeated process. So we arrive here with a bunch of nodes and the degrees thing. So we want to do we want to create 2 more nodes. I mean, for each node, we want to create 2 connections. We can like generate 2 random numbers right away, or we can have a loop and generate one and then the other. And there is a tiny difference because like once the network is large and we sample 2 random nodes, most probably they will be different, right? Once you have 100 of numbers, the probability of hitting the same number twice is like about 1%. So it's pretty small. But early on in the network evolution, if we sample them randomly, then we can sample the same. Oh, I'm actually, no, it's fine, it's fine, it's fine. I suddenly remembered, it's fine. So, okay, look, if we just sample them randomly, then the probability of sampling the same node will be rather high. However, if we go and check the description, where is it? The description of numpy.random.choice, it's actually awesome because it also has replace parameter, and by default replace is true, which means that as you are sampling from this list, you can sample the same thing twice, but you can set replace to false, and then it won't sample the same thing twice. At this point, I feel like I need, you know what, I probably need to show you how it works. So let's have a little test ground above. Test ground for this thingy, numpy.random.choice. So let's say we have a is like 1 2 2 1 2 2 3. numpy.random.choice a. If we just do this, okay, let's do a loop for I in range 10, print this thing. And actually, yeah, let's have them not in different, let's just write all of them. Yep. See what's happening? So it's sampling randomly. Good. And if we keep doing that, you can see that in this case, there are more 2's in the list because 2 is overrepresented, so it is more likely to be sampled. So that's one option. And that's the option I decided to not pursue, actually. Sampling from a list with some values overrepresented. Option 2, sampling with different probabilities and no replication. So what do I mean here? A equals 1 to 3 for I in range 10. Let's repeat it 10 times. Print and p random choice a. Okay, so how's about instead of sampling one element, we'll sample 2 elements. Size, nope. Size equals 2. Oops. Oh yeah, of course. Okay, so now every time we sample 2 elements, you know what? Let's go wild. Let's sample 3 elements. So if we sample 3 elements, as you can see, we can still have different configurations, and sometimes we can even sample the same element 3 times because by default it samples with replication, which means that when it takes something from this list, it doesn't actually take it from the list. It just picks a random number. I mean, picks a number element, a random element, and then it picks another random element, but it can pick the same random element again. However, if we change it to replace equals false, then now it doesn't do that. And if we do, so if it sampled 3, it cannot sample 3 again. It has to sample either 1 or 2. And then once it, in this particular case, if it sampled 2, then it's bound to sample 1, right? Because we gradually exhaust the list. And that's actually what we have. I mean, what we want. That's actually what we want to have in our model, because we really don't want to try to connect to the same node twice. Because in a normal graph, it's not a thing. Two nodes are either connected or not connected. They cannot be connected twice. There are special graphs called, I don't remember what they're called, but some, like, you can introduce a mathematical thingy that has double edges, multi-edges, so where two nodes can be connected with several edges, which is usually the same as saying that, as a weighted graph, as saying that in a graph some edges are more strong than others. So some edges will be like worth of 1 edge, but some edges will be more powerful and worth of many edges, like 3, 4, whatever. And it's a useful thing. Like if you think of a graph of how roads are like connecting cities, some roads have higher capacity, some roads are really tiny. So weighted graphs are really important. And in our network, we can use weighted graphs if some people like see each other often and some people see each other all the time. So we totally can go there, but we don't want to go there just yet. So for now, we really want all edges to be unique. The node number I is either connected to the node number j or not, which means that during sampling, we really don't want to like draw the same node twice and try to connect 2 times to the same node. So we'll be actually using this function with replace equals false. So what will happen if we try to sample more elements that we can? We'll get an error, right? With replication, because you cannot sample 4 elements from a list of 3 if you only use each of them once. If you don't care about whether you use each of, like how, like if you can sample repeatedly, if you do it with a replication, you can sample 4 from a list of 3 totally. But if you sample without replication, then sampling 3 from a list of 3 is the maximum number. It's kind of obvious, right? But we'll actually sample 2 from lists of various sizes, so that's kind of what we want. Oh yeah, we haven't tried probabilities yet. So let's try the vector of probabilities. Vector of probabilities, for example, p equals, so let's say we have 1, 2, 3. Let's say we will sample 1 with 50% probability. We will sample 2 with 4% probability, and we'll sample 3 with, no, I mispronounced that. 1 with 50%, 2 with 40%, and 3 with 10%. So let's see. Does it look like it's sampling properly? So if it's sampling properly, okay, let me make it more skewed. 7, okay, like 6, 3, 1. So if it samples properly, then 1s should be frequent, 2s should be slightly less frequent, and 3s should be even less frequent. Do we have it? Yep, we have it. That's actually weird. I don't think, is it true? I mean, yeah, so this, it's okay, so it will work. What I was thinking about is, I think these probabilities are kind of in conflict with the idea of sampling with no replacement, just because if we sample 1 with high probability, so the frequency of numbers in this list won't actually match these probabilities, because if we sample 2 elements without replacement from a list of 3 and we already sampled 1, then we're bound to sample either 2 or 3 for the next point. So these probabilities will be true for the first position, but for the second position it will be like 2 will go with probability of 75% and 3 with probability of 25%, because we'll have to renormalize this thing, but don't worry about that, like whatever. It's still the best approximation of what we need, because again, all of this stuff with not connecting to the same node twice is really only relevant for the very early phases of our network creation, when we have fewer nodes and the chances of drafting the same element twice are high. But we actually want, like for our models to work, we want our network to be kind of large. And once we are in the hundreds of nodes, it doesn't matter. The probability of drafting the same node is pretty low. So we could actually even not do any of this fancy stuff. We can just try to connect to 2 nodes and just ignore nodes, ignore those cases when we drafted the same node 2 times, and it will still be fine. So I'm kind of making things almost unnecessarily complicated here, but I also want to, I don't want to give an impression that I'm lying. So I don't want to code something that's actually explicitly untrue, even if it doesn't matter. So let's try, let's do this thing. So let's call it like candidates. This is nodes to connect to. Candidates, bad name. New connections equals np choice connections is fine. Connections np choice. We're sampling from the list of nodes. We don't have it yet. It's essentially like, okay, let's just have it, nodes. And we'll start with, so let's nodes equals 0, 1. So by the time, so when we're done with node 1, once we have node 0 and node 1 and we are ready to go for the loop, we need to prepare everything. So we'll create nodes, and originally they will be like 0 and 1. So connections, we choose from the list of nodes, and we want to sample 2 nodes just because that's the network we are doing. And we want replace equals false, so we want both of these nodes to be different. And we want the probability to be equal to degrees divided by np sum degrees. Right? Right. So that will be the list of connections. And we'll connect our new node I to these new connections. So we'll do like, okay, for node in connections, this loop will only run for 2 loops, for two times, but I still don't want to type the same thing twice, so I'd rather use a for. So for node in connections, we connect to this node, then we set degrees for this node. Increase degrees for this node. Degrees node plus 1. Right? Right. And then we also update degrees for the newly added node. So degrees for newly added node I is equal to 2 because it got connected to 2 new nodes. And we should also add it to a list of nodes. Okay, nodes append I. That's a better way to frame that. Right? I think so. Okay. So let's try that. Let's add, like, let's look under the hood. Let's do print I and nodes equals nodes and degrees equals degrees. And let's create a really tiny network. So it will be called Barabasi. Let's look at the network of 5. And we will make a picture of it. And that's all we need. Okay, sure. Let's leave the other part as well, but without that and without that. Okay, something doesn't work. What doesn't work? Barabasi. Why? Oh, okay. Degrees equals numpy array. Oh yeah, why numpy array should be np array. Still something doesn't work. Local variable nodes are right, because I decided to be smart. It wasn't a good idea. Nodes was equal nodes. Okay, let's do it like properly, because at I equals 0 nodes didn't exist yet. Sure, nodes are empty here. Nodes append 0, nodes append 1. Let's make it read more logical. Okay, so now it ran for 0th point. It totally crashed. Oh, we cannot add new elements to degrees like that. This will also cause an error. So we need to actually append. Sure, we can do that. So degrees of 0. So we cannot, if you have a vector in NumPy, an array, you cannot just address a thing that doesn't exist and assume that it will pop to existence. It gives you an out of bound error, this one. So for the existing node, we can update its degrees. So this will work, and this will work too. But when we're adding a node, we should use something else. So let's use append. Append, and here we append 1, and here we will append degrees, append 2. So it will create a new entry, and it will have a correct position, just because of the way we are creating it, and the value will be 2. What doesn't work here? Oh yeah, because oh Lord. Yeah, because I created it was empty. It wasn't just sure. So here we also need to have append degrees, append 1. So we need to append 1 2 times for node 0 and node 1. We cannot append. Ah, okay. Append works for a list. It doesn't work for numpy array. Am I annoyed at that? Okay. All right. You know what? Screw that. Go back, because we know the number of nodes. So let's just create an empty list of, so append is good for lists. For NumPy, it's better to pre-allocate space. Sure, we know in advance the size of this thing. It will have n nodes in it. So let's just create it, fill it with zeros, which will totally work. No, it won't work. So if I do that, I can update degrees, but then this part will stop working because It's okay, I'll fix it. So it will stop working like that because nodes will be shorter than the degrees, because the degrees will be always the full size and the nodes will only have the nodes that we had so far. But we can fix that. We'll just correct the size here. Okay, so first thing first. So degrees is a vector of zeros. And then back to the previous thing. So we just will be updating values. So degrees 0 equals 1, degrees 1 equals 1. That's for this part. This part is true. And here, oops, degrees I equals 2. Because it's a new node with 2 connections. But if I run it now, it will run for 2 special cases, but it will fail here because it says, oh no. Oh, it failed for a different reason. It says no choice in numpy because it's a random choice. But once I fix that, now it says A and P must have same size. And here A is the number of nodes previously created, it's short, and P is the full thingy that's pre-allocated. So let's just slice from it. Let's only use first few nodes. So for example, when I equals 3, we'll only use first 2 entries into the degrees vector. And we can still divide by the full sum because all other entries are zeros. So yeah, this should work. It still doesn't because I have a mistake. Connectins is not defined because it's connections. Okay, now it works. But before we enjoy that it works. Okay, no, let's enjoy that. Enjoy the workinesses of it because it works. So let's first look at the logic. We had 0 nodes. Okay, no. Okay, here's these things are outputs of this line that I added, and it shows the kind of step, the nodes by the end of the step, and the degrees by the end of the step. So by the end of step 0, we had only one node named 0, and all degrees were 0 because it wasn't connected to anything. Oh, you know what? I can actually, the better way to do that is like also to do that. So here's how the network looks after step 1. After one step, namely step 0. One node named 0, not connected to anything. If we do 2 steps, then we add a node to it, and that's it. But starting with 3 steps, we are starting having these new nodes, and they're randomly connected to the existing nodes. Except if only 2 nodes exist, then there is nothing random about it. You'll always have a triangle. So you always have, by the end of step 0, you have node 0 and 0 degrees. By the end of step 1, you have 2 nodes, 0 and 1. And 0 has 1 connection, 1 has 1 connection, and the third doesn't exist yet. By the end of step 2, we have 3 nodes, 0, 1, and 2. And all of them have degrees of 2 because we have a triangle. By the end, if we do 4 steps, we will have always 4 nodes, and 2 of them will be connected to 2 other nodes, and 2 of them will be connected to 3 other nodes. And the graph itself is always the same, but it will be represented in, like, there are 2 ways to draw it, either like that, or sometimes we may have, am I lying? Why doesn't it show the other configuration? Oh, this one, yep. So, but this is actually the same. It's still 2 nodes with degrees of 3, 2 nodes with degrees of 2. So up to this point, the network is fully deterministic. But at next point, as you can imagine, we can have two slightly different things. So the new node can either connect to one of those edges, and then we'll have like a little triangle growing from here, and we'll have one node of 4 and one more node of 3. Or it can connect to this edge, and then we'll have 2 nodes of 4. Or it can connect to this edge, and then we'll have 2 more nodes of 3. So starting from 5 steps, we can actually have two slightly like I think it's 3 different types of networks. And if you look at the plot of degree distribution, you can see that it kind of oscillates between different configurations. There are only 3 or 4 configurations. So I reran it, I got the same thing. This is a slightly different thing. It looks like a bridge. This is actually also a bridge, even though it doesn't look like a bridge. And sometimes we have this thing with over-connected nodes of 4. No? What? Ah, no, I'm lying. It's okay. Yeah, so this is actually without nodes of 4. This is with the nodes of 4. Anyways, seems to be working, right? Seems to be working. And let's rejoice now in that here's a network of 10. And you can immediately see why it's so cool. I mean, why it's so cool. Yeah, you can immediately see why we did that. We have a node here in the middle that has a degree of like what? 8. Look, we can use the diagram. It has, so that was probably either node, oh, we can check. It's either node 0 or node 1 because they were born earlier. Oh, look at that. If you look at the degrees, it's actually the node number 0. So it's the very first node to appear. And it was always in this really privileged situation. It appeared early, and so it could accumulate connections from the very early on. And so, but the more connections it accumulated, the more likely it was to get more connections because of the way we build it. And so by the time we created 10 nodes, 8 out of 10 are actually connected to it. And then we don't have nodes with 7 connections, but we have a node with 6 connections, right? This one. If we go to higher networks like 20, okay, my textual printing is not helpful anymore, so let me comment it because it was good for debugging stuff. Look, we have this node in the middle still. Well, in this case, it has only 8 connections. Let's rerun it. 11. See, we have a node with 11 connections. I bet it's this one, but it's getting hard to see. 50 nodes. Yay! We have a node with 16 connections. It's one of those 2 nodes that's somewhere in between. It's like because we have 16 and 15, probably like this one is 16, this one is 15, or the other way around. But it works. So it works. It doesn't break. It works properly for a small number of nodes. And we can see that it has the property that we wanted it to have. It have this over-connected nodes. And if you look at the distribution of degree distribution, so what number of nodes had we tried before? We had actually tried 100 nodes. So look, for a random network, for RDosh network with 100 of nodes, the highest degree was 7. Oh yeah, but it's not true. I mean, we had the same number of edges. Okay, let's modify that. We cannot compare them now, right? Because RDosh had fewer edges. It had the same number of edges as the number of nodes. And now we have about 2 times of edges than we have nodes. So let's change this network creator as well. So if the number of edges is exactly 2 times the number of nodes in a random network, the most connected node is has a degree of about 11. 10 maybe 11, maybe 9, maybe 9, maybe 10. So about 10, right? This one, like, let's skip the rich club network because, like, whatever. But for this network, for the Barabasi network, if we do 100 of nodes, the most highest connected node has a degree distribution of like 23. Look at that. Or maybe 22. Or maybe 27. So the degree is very different. The degree distribution is very different. We have this really long tail, and most of these numbers are not occupied. So in this particular rendition that I got here, there is a node with 20 connections, but there are 0 nodes. It's 21, 22, 23, 24, 25, 26, but then there is a node with 27 connections. So this long tail doesn't mean that there is a node for every potential number of connections, but there are nodes that are really out there, like, you know, Oprah Winfrey's and Beyonce's or whatever, PewDiePie's of this little world that we created. Except they have a terrible fate because we'll expose them to a pandemic pretty soon and they will spread it. Yep. That was dark. Didn't mean to make it dark. All right, so last comment before I make a break, and because like we still need to run a pandemic on that, but I will at least, yeah, I will have a short break because I want to split it into 2 videos. But before we do that, I need to comment on something. Yeah, I wanted to comment on my code. So I'm not particularly happy about this code. And it works correctly. It's not pretty, and it has 2 issues with it. One issue is like these 2 lines. I think I can change look, I can add line numbers. So lines 20 and 21, I'm not happy about that because I have a vector of degrees, so lots of numbers. And I have another array with lots of numbers, with nodes. But somehow, for degrees, I pre-allocated it, and then I'm just changing the values. And for nodes, I'm adding them one by one. Moreover, I use different objects for them. For nodes, I use a list, and so I add to this list using the append method. And for degrees, I use a numpy array, and I'm changing the values of it. It's not wrong, but it feels a little bit odd because I'm using 2 different instruments that are not fully compatible, that are pretty similar, but not fully identical, and it's just potentially it's a breeding ground for misunderstandings and mistakes. I'm not quite sure how to make it better. If I knew how to make it better, like on the fly, I would have made it better. Maybe I should just pre-create nodes the same way I pre-create degrees and also slice them here only. Maybe that's a better way. Oh, you know, maybe that's a better way. Maybe I should do that just to be consistent. Should I? Yeah, you know what? Why not? Let's do that. Nodes equals np array range n nodes. So I'm just creating all of them at once, which means that I don't need to do that. I don't need to append anything to it. I don't need to do that. I don't need to do that. And to make it work, I need to change here instead. So I need to basically do this thing the same. So this thing now mirrors the thing I do for degrees. Oh, that's good. That should work. So it still works. It still works for small values. See, it works. It still works for large values. Okay, so instead of commenting on my code, I actually improved it. Right, because the second issue that I had with this code was the part where, like, there were points where I referred to a list of nodes, and there were points where I assumed that names and nodes are actually numbers, like here, for example, because I give here a number and not a name. Like how to put that in words? I have a list of nodes, but I'm also like I was of a double mind. I had a list of nodes and I pretended that I keep track of what nodes I added, but also I always knew that my list of nodes are actually consecutive numbers from 0 to I minus 1 included. And that just felt odd. But now I fixed that as well, kind of. So it no longer looks odd, because now all the code is written with an assumption, essentially, that the names of our nodes are numbers from 0 to n nodes minus 1. And it looks more coherent. So it's fewer chances for a person to get confused. And the person we really don't want to be confused is us in the future, because your main collaborator in life is you from another time, either from the past or from the future. So we really want to write in a way that's kind of makes sense and that you can intuit if you have to return to it in a month or a year from now. And you're like, what the heck? So you want your code ideally to be written in a way that you can read it and understand it. All right. So a small break, and then after the break, we do the actual propagation of this network.